Hello, welcome to the course on audio signal processing for music applications. This week we're talking about quite a few spectral modeling approaches. We are combining the sinusoidal and harmonic analysis that we talked in the last few weeks with the idea of residual and stochastic approximation of this residual. So in this demonstration class, I want to talk about one particular model, the harmonic plus residual model. So the idea of analyzing the harmonics of a sound, subtracting them from the original signal, and obtaining the residual, which then can be combined, of course, with the harmonics that we have identified. So let's use the SMS tools that we have been talking about and developing in the course, and let's start with the DFT, and let's start with a sound, with this organ sound that we have in the SMS tools directory. Let's listen to that, and we'll listen with headphones so that we can listen more carefully. Okay, so this is a quite very stable tone, and it's a very traditional standard sound of an organ. So in order to analyze, we want to be able to distinguish the harmonics of this sound. So this is a C3, which is around 264 Hertz. So in order to find what is a good window size, well, let's use the Blackman window. This is a very stable note, so we can take advantage of a longer window and really try to isolate the harmonics as much as possible. So that's 6 beats for the Blackman window, and then sampling rate is 44,100, and then we divide by the frequency of this note, 264. So that gives me 1,002 samples that make sense to analyze. Okay, so let's put 1,003 to make it an odd window, and okay, let's use 2,048 FFT size, so with quite a bit of zero padding. That's good, and so let's compute it. Okay, so this is the samples that we are analyzing. We are analyzing 6 periods of the sound. It clearly looks very sinusoidal, and from the magnitude spectrum we see that there is not that many clear harmonics, even though there is quite a bit of energy in the high frequency range. But it doesn't have all these clear sinusoids. So this is an indication that it's a sound that has quite a bit of kind of a noise-like or kind of a stochastic component into that. Well, the phase looks as expected, and of course the reconstruction is quite good. Okay, so this looks like a decent approach. Of course, we could maybe, given that is stable, we could take a bigger window size. So let's try that. Let's try like twice as much. So let's try 2,006 samples, and then let's even do a bigger FFT. Let's use 4096. Okay, so we are doing quite a bit of zero padding, and well, here the time was in 2 seconds, which is good. The sound is quite long, so we're kind of in the middle. So let's do that. Okay, this looks twice as many samples, like we are analyzing like 12 periods. And yes, now we are seeing a little bit more things in the spectrum. If you compared the previous one to the current one, we are seeing the harmonics maybe more defined, and we are seeing quite a bit of background things. So maybe now we are seeing a little bit higher harmonics than we were seeing before, because with the higher window we kind of reduce this background because it's not a very coherent type of signal, so it emphasizes the coherent parts, the harmonics, and reduces this kind of stochastic component. Okay, so this seems to be a good choice. So let's go to the STFT and apply the same parameters. So let's apply the Blackman. Well, let's first open the sound, the organ sound. Let's use these 2006 samples that we took, okay, and let's use the 4096 FFT size. Here now we have to choose a hop size. Well, here I don't think it matters that much, but let's just use maybe 500, so 1/4 to be able to overlap with the Blackman. In fact, it should be even more, but for efficiency purposes, let's just leave it like that. Okay, let's compute this. This will take a little bit longer because, of course, it's a longer sound and FFT is quite big. Okay, so this is what we are getting. Of course, the resynthesized, no need to listen to it because it's going to be quite identical. And now, well, we see the horizontal lines. Maybe let's zoom into the lower areas. Okay, and so that we can see a little bit better the harmonics. The harmonics look clearly very well defined, but there is quite a few things in between. Okay, that seems to be a good choice. Now let's do the harmonic analysis, again using the same parameters. So we'll go to the organ, let's say the Blackman, let's use the 2006, and let's use 4096 as the FFT size. And now we have to choose the parameters to identify the peaks and the harmonics. The magnitude threshold, okay, -90, that looks like a reasonable one. The duration of the harmonics here, since we are in a long stable node, we can even afford to put longer type of tracks, or at least let's say that they have to last for 0.2 seconds, or it could be even more. The number of harmonics, the truth is that there is not that many because they kind of disappear. So I would say that with 30 or 40 harmonics should be plenty. And we know the fundamental frequency, 264, so the range has to be for that. So 130 and 300, 264 is within that. So maybe we can even make this higher so that it makes sure that it fits correctly. Okay, that sounds good. And this is the error for the fundamental frequency detection. I mean, it should be a very clear fundamental. There should not be a problem with that. And this deviation, this is how we will allow the harmonics to deviate from perfect harmonicity. So let's leave it like this and see what happens. Okay, let's compute it. Again, this will take a little bit longer. Okay, so we found quite a few harmonics, and of course in the attack and decay is very unstable, so maybe we should have rejected those. But what is interesting is that some harmonics are quite stable, but some are very unstable. Let's listen to the resynthesized sound. Okay, it sounds good. Let's compare with the original. Well, if you pay attention, clearly the original has this more air in the background that is not in the synthesized because it's only mainly the harmonics. But the truth is that also some of these higher harmonics are very unstable. So maybe it's not right to consider them as harmonics because they are basically maybe tracking some noise part. So one way to get rid of that is to reduce this deviation and restrict it even more. For example, let's put 0.001 and then let's see what happens. Okay, now it got rid of some of these partials, But maybe an even better way to do that is to make sure that they are long enough. So instead of having 0.2, let's make sure that that the harmonics should be at least 1 second to be considered. Okay, now we got rid of quite a lot of these higher unstable either harmonics or components. Let's listen to the synthesized sound. Yeah, that sounds quite clean and definitely of course not as rich as the original sound. Okay, now we can go with these same parameters to the harmonic plus residual, so to subtract these harmonics from the original signal. So let's use the same sound. Let's use this 2006 window size, 4096. The threshold was minus 90. The minimum duration of track, I think we put 0.4 or we put 1 second. So okay, so 1 second. Number of harmonics, now definitely we can put less, we can even put just 30. And here we have to make sure it is within that, so let's say 130 to 350, so that is within that. For sure it will find it no problem. And error, I don't think this matters too much, but here we put 0, 0, I think that's 2 zeros. Okay, we'll leave it like that. Okay, let's now compute this. Okay, this is what we got, and let's see. So here we see the harmonics it found, the black lines, and the background spectrogram is the residual. And we can listen to the different components. So we can listen, well, just the sinusoid, the harmonics, we already heard that. Let's listen to the residual. Yeah, that's a very clear and nice sound. That is what it was missing from this harmonic sound. So clearly, if we put these two sounds together, they will sound like the original. Compare it with the original. Yeah, that's an identity basically. So this was a good sound to explore the potential of the harmonic plus residual. Of course, if we take time varying sounds, that may be a little bit more tricky, and we will have to tune the parameters a little bit more. But with that, I think you get an idea of what the harmonic plus residual model and the tool within the SMS tools that implements this model, what it can do. So I encourage you to play around, of course, choose other sounds, maybe more complex sounds and sounds that change in time. So we have talked about the harmonic plus residual model, and this is one instance of the models that we are talking about this week. On the next demonstration lecture, I want to talk about the harmonic plus stochastic model, so that we can model this residual that we just heard as an stochastic signal and see what it can do. So I will see you next lecture. Thank you.